So in a vein similar to what Francis told us about this morning, we're interested in trying to understand something about the training and performance of neural networks. And so I've got a diagram here that's kind of similar to Francis's, but I helpfully used all different notation just to keep you on your toes. So we're interested in a network that's going to take a d-dimensional input and output a single real value. And the way we think about this is the following. All the parameters of this network is one giant vector that we'll call theta. So this corresponds to the weight matrices at all the layers plus the final layer. And we can think about the output of this network as some function h that is a function of the input x and is characterized by these weights in theta. So we take the input x, we multiply it times the first weight matrix W1, apply a nonlinear activation, and so forth. And then finally, when we want to train one of these networks, we would take some data and a loss function, and we would try to choose these weight values to minimize some loss. And so the question that I'd like to think about today is what happens when we actually do this with a real data set? What are the generalization properties, and can we better understand why these networks seem to generalize as well as they do? Especially when the number of weights, or the size of this vector theta, is very large relative to the amount of data that we have available to us. And there's been a flurry of work recently in trying to understand what happens when we try to do learning in an overparameterized regime. So this is a diagram from one of Misha Belkin and Daniel Su's paper on overparameterized models. And it's the result of some experiment on the MNIST data set. And they show that even as the number of parameters that have to be learned grows way beyond the size of the data set, the holdout performance can often be quite good. And so we'd like to better understand this phenomenon, especially in the context of neural networks. Now, the way this plot is drawn, the horizontal axis is the number of parameters, the size of this vector theta. But it's not so clear that that's really the quantity that we should be thinking about. And in fact, way back in 1996, Peter had this great paper that told us that if we want to understand something about the generalization of neural networks, then we don't need to think only about the number of parameters, but we really need to think carefully about their sizes. And so going back to this original setup, we're going to try to understand something about the generalization of networks. And in that vein, think very carefully about the sizes of these different parameters. Okay, now as Francis was telling us about this morning, and Lorenzo, in many of these training regimens, there's some sort of implicit regularization going on. And so we're actually going to make it non-implicit in this discussion. And we're going to look at this variant here, where we're trying to minimize the loss plus a regularization term, C of theta. And the particular regularizer we're going to consider is the sum of the squares of all the weights. And so what we'd like to understand is how the generalization performance, ultimately, what we can say about generalization for this kind of regularized risk minimization. Okay, so first of all, let me just show you a little experiment here where I'm going to have just a single hidden layer with 200 units, and all my training data is in 2 dimensions. And I'm going to take 10 different points, which I've plotted here, and try to learn a function h theta of x that is a good fit to all these points using this regularized cost function. And so I start with some initialization, and I go through some sort of stochastic gradient descent training regimen. And after doing this for a while, I end up with a function that perfectly fits all of my 10 data points. But of this function, even though I have 200 ReLU units in the middle, only about 5 of them have pretty substantial weights. The remainder have very small weights and are really not playing a significant role in specifying this function h. Okay, so as I said in the title, we're not going to look only at sort of this parametric view, thinking about how these things perform in terms of theta, but we're going to take a function space perspective. And this is what I mean by that. So the way I set this up earlier is I said we've got this vector theta of all the parameters of our neural network, And we're going to try to learn good parameters by minimizing a cost function over theta. But we can think about this from an equivalent perspective, where what we want to do is, in fact, learn a function f that is a good fit to our data wherever we have an observation, and is a small regularization term. And what I want to do is I want to think about this process of how neural networks behave through the lens of this ladder function space perspective. So it's very easy to say what this regularization term in function space would be in terms of these original parameters. So in particular, what we could do is we could say the regularizer for a function f corresponds to looking at all different functions that my neural network, or all different parameterizations of my neural network that could produce this function f, and then choosing the one that minimizes my parameter space regularizer c of theta. So if I know c of theta, I can specify my regularization on f in terms of c of theta. Okay, but that's not especially intuitive. And so what I'd really like to do today is to try to dig into what this regularization function is. So we know something about how to choose parameters in neural networks. And what is happening is that we are implicitly regularizing the functions that we are fitting to our data. And the question is, what is the regularization over this function space? Which kinds of functions are preferred or not preferred, as opposed to thinking about it in terms of which weights are preferred or not preferred. Okay, so this obviously is not done in isolation, and people have thought about trying to understand different properties of networks for a long time. From an approximation theory perspective, there was some early work in trying to understand what functions can be approximated by neural networks, and of course they're universal approximates, and so almost any continuous function can be approximated. But then you could say, all right, how many different units do I need in order to get an epsilon accurate approximation? So if I want to find some h theta that is within epsilon of f, then how big does my network need to be in order to make that approximation? And there's been quite a bit of work in that vein as well. But the question that we're asking today is a little bit different than these. Instead, what we'd like to ask is, what functions can we represent if we say that we want this function space regularizer, R of f, to be bounded? What is that space of functions? So we can write down R of f in terms of the parameters theta of the neural network, but we'd like to say something a little bit more about how this corresponds maybe to other function spaces that we know something about, like Sobolev spaces or other kinds of properties associated with these functions f. Now, for some technical reasons, we're going to actually ask a slightly different version of this question, which is, which functions can be epsilon approximated by a bounded norm neural network for any epsilon for a slightly different regularization function R? So in particular, I'm going to define this new regularization function R bar of f, which says for any epsilon, I'm going to consider all of the possible functions that my neural network can represent and only consider ones that are within epsilon of my target f. And among those, try to minimize this cost function on my weights. And then I'm going to look at the limit of that as epsilon goes to 0. Okay, so this is a slight variant on this notion of function space representation that we're interested in. And this is the function that we'd like to understand. Or we'd like to understand, well, what's the space of all the functions for which this R bar is lower than some bound? Okay, so to get at this, similar to what Francis described this morning, we're going to focus on two-layer ReLU networks. So we've got a d-dimensional input and then some arbitrary number of middle layers, or middle nodes, and then finally an output. And so I'm going to switch up the notation a little bit since we only have two layers. And the way we can think about the output of this network, h theta, is we would sum over all the different middle nodes. Each middle node has got a weight, alpha, associated with it. And then that weight is multiplied times the output, the ReLU function applied to the inner product of our input x and some weight vector wi, plus a bias term beta, or b. Okay, so in this special case now, we can write down our regularization function, c of theta. It's just the sum of the two norms of all the wi's plus the two norm squared of alpha. And we've got this r bar regularization function that we want to understand a little bit better. And so the main goal of this talk is to try to understand what this function r bar is. So in particular, it is possible to show that this corresponds to a norm, and we'd like to understand what is that norm in a more explicit way, instead of going through this c of theta. Okay, so there's been some earlier work in this vein that focuses specifically on the case where the input is one-dimensional. So if we only consider functions that go from r to r, from the real line to the real line, then it's possible, and in past work, my co-authors derived an expression for this r bar of f, and it is the maximum of the L1 norm of the second derivative of the function, and the absolute value of the way the function's derivative behaves at negative infinity and positive infinity. We can actually make a small little modification here to simplify things quite a bit. So what I'm going to do is I'm going to take that original network that I was looking at, and I'm going to tack on to the end an unregularized linear unit. So I've got v inner product with x that gets added on to the end of my h theta function. And with that small modification, which is consistent with a lot of practice, we can more easily express this regularization function, r bar of f, is simply the L1 norm of the second derivative of f. So another way of saying this is that if I have a two-layer ReLU network, and I want to fit data from a one-dimensional function, so 1D outputs to 1D inputs to 1D outputs, then learning that function where I do some regularization on the neural network weights is equivalent to, in function space, regularizing on the smoothness of the function in terms of the second derivative's L1 norm. Okay, so let me just show you a quick little picture of this in 1D. If we wanted to fit these data points, then the function f star that is the best fit in terms of this regularization function is simply an interpolating linear spline. Okay, so I want to tell you a little bit about some of the ingredients from that analysis that we're going to leverage as we start going on to higher dimensional inputs to these networks. So we're starting with at the same starting point. We've got the same specification for the network and the same kind of regularizer that we had before. And one of the results from past work that, I'm sorry, I'm missing the reference to, says that this regularizer that we've been considering before, where we would minimize over all possible thetas, trying to find a parameterization of the network that fits our function and minimizes the cost function over thetas. This is equivalent to saying I'm only going to consider networks where the collections of weights going into any particular blue node in the middle, that's got a norm of 1. And if I impose that constraint, then my regularization function amounts to minimizing the L1 norm of the alphas, of the weights in that second layer. Okay, so these are two equivalent ways of writing this function space regularization term. Okay, so we're going to use that equivalence. And we are also going to let the number of nodes in the middle layer start going to infinity. So we're going to say, well, we're not that interested in how many different nodes are in this middle layer, like I talked about before. We're really interested in how big the weights are in the network. So as we go to infinity, then we have this sort of continuum model that I think also appeared in Francis's talk, where we can write the function represented by our neural network as an integral. So in this integral, I've got, instead of discrete weights alpha over each node in the middle, I've got a measure, alpha, over a continuum of different nodes. And each one of these nodes in the continuum has a weight vector times our input plus or minus a bias, and it goes through a ReLU network. And so then we can integrate over all weight vectors that have unit norm and all biases B. Okay, so all we're doing here is we're thinking about taking this network and thinking about what happens in the limit as we allow the number of middle nodes to go to infinity. Okay, so from this perspective, combining this integral representation corresponding to an infinite number of nodes, plus the alternative way of writing our regularization function, results in this expression down at the bottom, where all we need to do to think explicitly about this regularization function in function space is to take this measure alpha that corresponds to our infinite width neural network and compute its L1 norm. Okay, so then the name of the game becomes trying to understand what this alpha measure looks like. And that's what's going to help us really characterize what this regularization is doing. So again, just thinking in the 1D case about what's happening here. Well, in the 1D case, the weight vector is just one-dimensional because everything's one-dimensional. And since we restrict the norm to be 1, then the weights just go away. And our integral function looks a lot simpler because there's no longer any weights. And so we've got this equivalence that we need our function f that we're trying to represent with the neural network to be the integral of alpha of b times x minus b sent through this ReLU activation function.
So
Yeah.
also b minus 1, the weight?
I'm sorry, what?
The weights could be 1 or minus 1.
Yeah, the alphas could be plus or minus 1, that's true. But I don't think, so yeah, there could be a minus sign in front of this, but that's not going to change the overall message. Yeah. But if we were to just use this as a starting point, then you can solve and find that the alpha that satisfies this equation is the second derivative of f, which is what I told you before was the regularizer in 1D. Okay, so that's how you could derive that this regularization function, r bar of f, is the L1 norm of the second derivative of x. Okay, so just as a little toy example, here is some sample, a sample function and its second derivative. And what we see is that you have these spikes in the second derivative corresponding to the 5 different ReLUs used to write down this function approximation. And the spikes are located at different BIs corresponding to where the ReLUs are biased. And the heights of the spikes correspond to the alphas, how much weight is applied to each one of them. And so then we could start thinking about you getting larger numbers of samples, and then we have larger numbers of spikes, and we're getting a better approximation to our function. And in the limit, as the number of nodes in the middle goes to infinity, then we've got our overall function and its second derivative. Okay, so that's what's going on in 1D. And now the question is, what happens if we've got higher dimensional inputs? And unfortunately, it's very interesting, but it's far from a trivial extension going from 1D to higher dimensions. So in particular, we start with this top equation, which is our main criterion. We want to try to find a measure alpha that satisfies this equation. Okay, so we're saying that the neural network, the output of it can be expressed as this integral of alpha times the ReLU output of W transpose X minus B. And what we want to do now is we want to figure out which alpha makes this equation hold with equality. Because if we know what that measure alpha is, well, we know our regularizer is just the L1 norm of that alpha. So figuring out what alpha is going to tell us what the regularizer is. Okay, so in order to do this, well, we're going to use a few tools that I want to introduce. The first is simply a Laplacian. So if I had a single ReLU function, f of x, then its Laplacian is simply the sum of its second derivatives in each of the different coordinate directions. And so I'm showing that both from like a nice 3D plots and from a top-down view. And so if I had a sum of different ReLU units, then I can look at the Laplacian of that sum, and what I get essentially would be a line in this plot of the Laplacian of the sum of ReLUs, a line corresponding to each one of the ReLU units. Okay, so we're going to use this Laplacian for the following reason. So remember that I started with this top equation, which is giving me an expression for what's output by the neural network. And what I want to do is I want to figure out what this alpha is that makes this hold. What's the measure over the space of different nodes in this two-layer ReLU network? So I'm going to compute the Laplacian of both sides of this top equation to get the second equation. And after a simplification, I get this final expression. The integral over all weights with norm 1 of alpha evaluated at the weight and the weight inner product with x. And this is a very special integral. This is something called the dual Radon Transform. And it's been studied for many, many years, and it's got a lot of beautiful properties that we can now leverage to try to understand what this alpha function is. So have any of you ever interacted with or know about the Radon Transform? Okay, so this is actually something that you probably have unwittingly come across in the context of medical imaging. So imagine you've got a brain and you want it to be scanned. So you would go to a CAT scan, and what the CAT scanner does is it's shooting X-rays through your brain, and it's measuring how much of that X-ray energy gets attenuated between the source and the detector. And it's doing this in a whole bunch of different rays. And so what we see in this picture here, each of the red lines corresponds to the path of an X-ray, and the white plot corresponds to the attenuation energy. And you can think about this as basically being like a line integral through this image. And then what I've plotted in this tiny little bar here, that column corresponds to this white plot where white corresponds to higher amplitude and black corresponds to lower amplitude. And now what I can do is I can just repeat this operation for multiple different rotations. And for each rotation, I get a slightly different attenuation plot. And each one I'm then putting in a different column in this plot. Okay, so this is a different way of representing what's going on in the image. In 2D, it is called a sinogram, but it extends to higher dimensions as well. And so you can think about this image here as each column corresponding to a different rotation angle, and each row is corresponding to a different one of these red lines, or a different offset from the origin. Okay, so it turns out then that this radon transform is super relevant to trying to understand this regularization in neural networks. So in particular, we've got that this weight vector that we've constrained to have unit norm. Once we do that, then we can think about this horizontal axis as basically telling us how that weight vector is oriented. And the line offset, or the bias for each one of the nodes, B, corresponds to this vertical axis. Okay, so now we can say, well, can we use this to understand regularization in neural networks? So what we derived a couple of slides ago is that the Laplacian of our function that we're trying to approximate or represent with our neural network is the dual of this radon transform. So we can write that as R star of alpha, and I'm going to talk about what this dual looks like in just a second. But based on this, you might start to get a little intuition about where we might be headed. So I've got, for instance, a function on the left that is a weighted sum of ReLU units, and then I look at its Laplacian. And if I think about taking this Laplacian and computing the radon transform, you could imagine that every time I'm doing a line integral through this Laplacian image, and the line integral is lined up with one of these Laplacian lines, then I'm going to get a big spike, right? And so my radon transform is going to have some big spikes in it, where each big spike is going to correspond to one of these lines corresponding to the Laplacian of one of the different ReLU units in my function representation. So based on that, you might think, oh, okay, well then maybe this measure alpha that we're going after that's going to tell us how networks are regularizing these functions, maybe I should think about it as the radon transform of the Laplacian of f. And that's very good intuition. If you just want to have a nice kind of heuristic view in mind, I think that's a good way to think about it. But technically, we need to do a little bit more work. So in particular, we said that we wanted the dual radon transform to equal the Laplacian of f. And the question is that really true if we were to choose alpha to be the radon transform of the Laplacian of f? And in fact, that's not exactly true. We have to do a little bit more work. Okay, so here I've got an expression for the radon transform, where again we're just doing these line integrals corresponding to different lines. And then I've also written down the dual of that, or you can think about this as the adjoint operator. And this, again, is exactly the integral equation that we had for the Laplacian of f that we talked about earlier. Okay, so there's a key relationship between the radon transform and the dual radon transform. They're adjoints of each other. They're not inverses of each other. But it's almost unitary. So in particular, if I take an image, G, and compute its radon transform, and then compute the dual radon transform of that, then what I get is something that's not quite G, but it looks like some sort of fractional Laplacian of G. Okay, so what I can do then is I can use that in order to get something that's more like the inverse of the radon transform. So here I'm showing the radon transform of some function G. And now if I just directly apply the dual to that, then I get a kind of blurry, ugly looking image. But if I do a correction, if I take the dual radon transform and then apply a correction corresponding to this fractional Laplacian, then I actually get my original function G back out. Okay, so I can use the dual radon transform to get a nice inverse that I can then use. So in other words, if I were to start with a measure alpha, that remember is characterizing how much weight I'm giving to different ReLU units in my network, and then I compute the dual radon transform of that, and then apply a correction, then that is going to give me my original alpha back after taking the radon transform again. And here's how I'm going to use this now. So we go back to where we started. Here's my representation of the function represented by my neural network. And I take the Laplacian of that, and I note that the Laplacian of that is simply the dual radon transform of my measure alpha. And remember, the name of the game is to figure out what alpha is, because the L1 norm of alpha is my regularization function. Okay, so we derived on the previous slide this relationship between the dual radon transform of alpha and alpha. And so I can use this then to say that from the Laplacian of f, I can actually figure out what alpha is with this nice, neat formula. And so that allows me to define what kind of regularizer is implicitly being used in function space when I regularize the weights of a neural network. So in particular, I can say that this R bar norm that we've been going after corresponds to taking my function f and computing a fractional Laplacian, and then computing the radon transform of that, and then computing the L1 norm of that. And again, now it sounds sort of like a kind of a jumbled mess perhaps, but I think if we go back to this slide, it's helpful to keep that sort of intuition in mind. So remember, this isn't exactly right because we had to do some corrections, but I think intuitively this is a helpful picture because it's really saying that this third picture on the right is indicating basically via its spikes where there are ReLUs, what are the weight vectors and the biases associated with each of the ReLU units that we need to approximate our function f. And so by taking the L1 norm of this seems like a sensible way of measuring the complexity of a function being represented by a ReLU network. Okay, so let me in fact show you a little example. Here we go. So here's a function. It's got two different bumps, one in the upper right and one in the lower left. And then I compute its fractional Laplacian, and so you can see a picture of that. And then I compute the radon transform of that, and this is alpha. And so what I'm arguing is that the L1 norm of this alpha image should be the way, is the way that we are implicitly regularizing functions when we regularize the weights of neural networks. Okay, now what we can also do is we can say, what happens if we sample from this density alpha? So if I just start, incrementally adding in new ReLU units and adding them up to form a function approximation. So if I sample from this measure alpha 2,000 different ReLU units and add them together, I get one approximation. If I add 50,000 different ReLU units, I get a closer approximation. With 200 ReLU units, it's closer still. Okay, so let's talk about some of the implications of this. So I've told you that we can characterize what this regularization function looks like. It gives us a sense of what kinds of functions are preferred versus not preferred by neural networks that have been trained with this sort of regularization on the weights. One implication of this is that we are doing something that is different than regularizing according to a reproducing kernel Hilbert space norm. So in particular, the regularization term that we've derived is a norm, but it is not an RKHS norm. And so if we are going to do learning with a bounded norm, two-layer ReLU network, then we are doing something that is different than kernel learning. This is not just simple, even in this infinite limit, we are not using a kernel just without using the word kernel. Another implication of this result is something called depth separation. So in particular, we could consider a specific function, f of x, which I've drawn in 2D, but this holds in general dimensions, which is a simple pyramid function. And using the tools and the machinery that we built up in this work, what we can do is we can show that if we were to try to represent this with a two-layer ReLU network, then it has infinite representational cost. So this R of f would be infinite. So not only do we need an infinite number of nodes, but it's also complex in another sense. On the other hand, if we were to suddenly bump things up to a three-layer ReLU network, then we actually only need a finite number of ReLU units to exactly represent this function. And so what this suggests is that depth is really critical to our understanding of how and why neural networks work. And that's not just something that we observe empirically, but we don't know if it's a limitation of the way we train or computational restrictions. Rather, what this result shows is that depth matters on a fundamental theoretical level as well. And so it's not just that if we could tweak our training algorithms a little bit better, then we wouldn't have to worry about deeper networks. There's still several different open questions that we haven't addressed in this vein. Everything I'm talking about here, for instance, is about exactly representing this pyramid function. But if we gave ourselves a little bit of wiggle room and said, well, how much does it cost to approximate this pyramid function within some accuracy epsilon, that we don't know. We don't know the representational cost of that. In addition, throughout this talk, I've been focusing on an explicit form of regularization where we just do squared two-norm regularization on all the weights in the network. But as Lorenzo was describing this morning, a lot of times this is accomplished implicitly rather than explicitly, and there's a wealth of work in this vein. And so an open question still remains to try to tie these things together and characterize what kind of function space regularization might be occurring when we don't impose regularization explicitly, but rather do it implicitly using the kinds of iterative methods that Lorenzo described. There's also some questions about how interpolation behaves. And finally, as I mentioned at the beginning, the real end goal here is to try to better understand regularization. And this is something that hopefully we'll be able to tackle a little bit more easily given the current work. So if you want some more details, and there are quite a few that I didn't talk about today, the paper is on arXiv and will appear in iClear. And I'd be happy to answer any questions right now.